Good day. Today we're going to review essentials about how the CPU plugs into the rest of a system or device and how all that magic happens in terms of connectivity with electricity and grounds and related issues. In our previous session, we said that there were three important trends that are playing out for CPU design. So most manufacturers are now creating reduced instruction set chips as opposed to complex instruction set chips. Every time you see reference made to an ARM chip, ARM is a type or category of RISC chip. It's a reduced instruction set. You'll find these in mobile devices where CISC chips like the Intel iCore series and AMD Athlon and PC series, Threadripper and so on, those are general purpose chips for general purpose computing. So when we talk about a die, oftentimes there's a lot of confusion over what a CPU means exactly physically. What most people refer to as a CPU is actually called a package. Here you see that the CPU die, and that's the actual physical CPU, is mounted within a package that fits into a motherboard socket, and that package includes all sorts of extra input-output connections. So when you see this, what you're seeing are two dies for a dual core processor, right? Meaning there are two physical dies, and in some cases there are multiple cores on each die. So this could, if each of these had as many physical cores, each of the cores are a full-blown CPU. So all of the components that you know of in the von Neumann diagram, the ALU, memory registers, and controller, that's in here. Each one of these is a CPU in its own right. So we have a 4-core processor. Some of these are hyper-threaded, meaning they are virtually multiplied. In most desktop and server systems, hyper-threading means that you can gain the advantage through some, I don't want to oversimplify, but basically what we have is a case where you have two virtual CPUs for every physical CPU. In very high-end servers and computers, the CPU design includes different multiples, like a 4 by hyper-threading or a 6 by hyper-threading, in which case if you have 4 physical cores, you'd have 4 times 6, you'd have 24 virtual cores, virtual CPUs. Now this memory controller that you see here is a special hardware component that we're talking about in CSC 410, the memory management unit. And essentially this is a specialized hardware controller that sits between the CPU or CPUs and the RAM. But in any case, the important thing to understand is that the term die refers to this actual physical chip, and that's where the CPUs or CPU cores are implemented in silicon, and there may be more than one of these. The entire physical arrangement with all the extra contacts and pins for connectivity, that's referred to as the package, and that's what mounts into the socket. So that's an important distinction. Sometimes consumers or students will call the entire computer a CPU because, well, it's the physical component that does all the computing, and unlike the display or the keyboard or the mouse, but that would be an incorrect term. So in any case, The third trend we talked about was field programmable gate array. These are malleable or flexible processors that allow you to adapt the logic gates as needed. And those were the three trends we reviewed last session. What I'd like to do today is talk about how a CPU connects to everything else on the system board or main circuit board of a computer or device. And just as you have lots of connectivity, you have 64-bit parallel connections with pins that connect a modern 64-bit CPU. By the time you get to a motherboard or a system board, those are very highly condensed traces of metal film, and so it's kind of like the roadway of a major metropolitan area. If you're looking at it from a helicopter, a 64-bit system board, it's like you have all these 16 lanes, 16-lane highway in a major city in the US. And there are places in the city where they all condense or come together, right? So they all consolidate together. And when those data paths consolidate together, that's referred to as a bus, a data bus. The important thing to remember here is that the north bridge part of the bus, or the front side of the bus, it's often referred to as the front side of the bus or the north bridge. So the front side of the bus, which uses a north bridge chipset, by design, these handle very high performance, very intensive data transfer rates. So the high performance portion of the system board or device circuit board is it's this region called the the north bridge or front side bus. The south bridge, that's standard input output devices. So that's where you're going to find all of these connected devices in a computer. Just remember that when it comes to the CPU itself, and in this diagram you have a pair of dual core Intel Xeon processors. These are server processors. You have the CPU, you have the memory slots, right? So the memory slots would be here. You have high-speed networking for servers. That's high-performance networking. It's kind of a special peripheral. In cases where you have artificial intelligence, supercomputing, and machine learning, you have special high-speed graphics controllers. These are like gaming controllers on gaming PCs. All of these are very high performance, very high speed, parallel pathways. Everything else, virtually everything else, mouse, keyboard, display, USB connections, standard hard drives, just general purpose hard drives, CD or DVD drives, all that kind of stuff. All the rest of the connectivity, sound cards, sound inputs and outputs, all that's in the south bridge, or it's not the front side bus, right? So whenever you're seeing descriptions of a data bus, if you see front side or you see north bridge, high performance. If you see anything else, it's, well, standard input output peripherals, and yeah, that's a general layout of how most system boards are organized. Now, one thing that's changed recently is that hard disks have increased in terms of their performance. So if it's a standard disk, yeah, it's on the south bridge, but solid state disks are now faster. They use a fraction of the power, but they're all built with NANDs. So when we talk about flash memory, USB drives, or solid state drives, the NAND logic gate is used in a big way to create that non-volatile memory. and it works better than traditional hard drives. So that's just something we should mention here while we're into it. One of the biggest things to understand about all of this is the flow of electricity and how that impacts the efficiency or reliability of motherboards and system boards. What's true is that the ground for electrical equipment is critically important. So in order to have a complete circuit, a digital circuit, you have to have a proper ground. And if you don't have a proper ground, then the whole thing can't flow properly. And so it's really important to understand that even surge protectors can't work unless there's a proper ground. A surge protector takes excess voltage and then basically redirects that into the ground, but if there is no proper ground, then the surge protector can't protect your equipment. The other thing that happens too is that the flow of electrons and the proper function of the digital circuits become impaired when you don't have a good ground. 30% of all hardware failures, 30% of all hardware failures can be traced back to poor grounds. And why is that important? Well, I want you to think of a system board as a device that's similar to a dishwasher. So if you had a garden hose and a bucket, or you had a dishwasher, you could ask the question, well, which one would make the quickest work and do the best job cleaning a dish full of dirt, a sink full of dirty dishes? If you had a sink full of dirty dishes, most people would say, well, of course, it's the dishwasher. If you compare the garden hose and bucket with a dishwasher, there are a number of things that are similar about them. Basically, they use about the same amount of water, and when you finish washing and dump it out, that water goes back to the ground table, the water ground table, right? But one of the differences in a dishwasher is that there are dozens, even as many as 100 highly directed streams of water where the flow and direction of that water is tightly controlled. And that's why a dishwasher is so much more effective. If you look at a modern computer system, there's a flow of electricity and it can get work done, but it's kind of like a digital equivalent of a dishwasher, where you have all these different precisely controlled flows of electrons, and at the end of the day you still have to have a proper working ground. You still have to have that ground. Well, we'd also like to mention while we're in here that there are other semiconductors like silicon. So, and you may have heard of graphite. So most of our chips are made out of silicon, but there are combinations of elements that are proving that are becoming a matter of interest. So germanium arsenic or gallium arsenic, gallium arsenide, you can get combinations of other elements that possess semiconductor qualities. So if you think about the dishwasher again, you're controlling the flow of water. You're not, it's not all coming through a hose all at once. It's not just conducting the water, it's semi-conducting the water. It's controlling the flow and direction of very small portions, highly directed streams. You can think of a semiconductor material doing a similar thing. Now I'm generalizing those, that's a generalization of these basic concepts, and it's important to understand that we're trying to make a very complex component. We're trying to describe it in a simple manner. Einstein said you can make everything as simple as possible, but not simpler. So we don't want to oversimplify to the point where we're drawing comparisons that would be, wholly inaccurate. But Essentially, it's helpful to use analogies, and I there's a lot of there's a lot of interesting similarities between water and electricity in terms of how it flows and what it does. And if you engineer the process well enough, you can get really clean dishes, or you can get computing tasks that are easy to calculate. So in any case, remember that it's the ground um, that allows semiconductors to do their work. And if you don't have a good ground, you're pretty much screwed. For this segment, we'd also like to call out some important names in the industry and developments along the way. You're already familiar with von Neumann, and as we've already stated, there may be different representations of the von Neumann model, but John von Neumann remains an important pioneer, and so we just want to come back to this. And there's another pair of gentlemen that worked with Texas Instruments. Now, Texas Instruments was known for creating handheld calculators. Before we had PCs and laptops everywhere, a lot of folks used calculators, handheld calculators, and Texas Instruments was, if pardon the pun, instrumental in developing silicon-based integrated circuits. And as they grew larger, the name of those integrated circuits, or ICs, changed. So the acronyms kind of evolved, where they were large-scale integrated circuits, L6, to very large-scale integrated circuits, or VLSI chips. And again, Jack Kilby and Robert Noyce were the first ones to create an integrated circuit. Gordon Moore was the co-founder of Intel, and he is the gentleman that came up with the idea that every 18 months to 2 years, the way the hardware industry is progressing and manufacturing techniques are progressing, the capacity and performance of many or most digital components is doubling. So it doubles every 18 months to 2 years, and that's known as Moore's Law. So what we want to do is kind of back up a little bit and take a broader view of motherboard design, and from a big picture, like the view from 50,000 feet, you basically want to know that you're always going to have these components. So this is the von Neumann model again, and here's another representation of the von Neumann model. If you get inside the CPU itself, there are important components that help the computer perform the waltz, the fetch, decode, and execute cycle that allows it to do this. And there's a part of the controller mechanism here that's called the program counter, and it has a special register that increments to the next instruction, because in RAM you're storing data and instructions, and it is this program counter in the CPU that allows you to move on to the next instruction, except for cases where there's a go to directive or a jump. So that's an important consideration about CPU configuration and how that works. Just remember that you're going to see a reference to a PC, and we're not talking about a personal computer. When we're talking about a component of the CPU, we're talking about the program counter. A common acronym or abbreviation for motherboard is MOBO, and front side bus or north bridge is often referred to as FSB, right? So south bridge, what you're going to see here for the rest of the study guide is that I'm going to restate in different ways much of the same content, with the intention that if you hear different descriptions and see different images of the same thing, it's more likely that the concepts will stick. So just remember that when you have many of the high performance 64-bit or 32-bit parallel connections, and they consolidate. Um, we call that a data bus, the bus. And when the buses consolidate, there's a junction point, we call that a bridge. So when you see different images of this, it kind of makes sense. So here's an image of an arithmetic logic unit, an 8-bit arithmetic logic unit. And so you see a set of pins or inputs, and outputs, right? So you have inputs and outputs. And basically what you can do by extension, if you take 8 bits and 8 bits and 8 bits and 8 bits, you have 16, then 32, then 64. So, this is just an extension of the same concept, so you can kind of visualize how massive 64-bit processors are, right? And how far they've come. That's an important part of this module. The other aspect that's really critical to understand here is this idea of the CPU package and how physically it contains the dies, which in turn have cores and other components. So each core is like an it's like a complete CPU with ALU and controller and registers. But you have so many of these 32 and 64-bit pathways, you need a great deal of connectors, and that's where these pins come into play. So here's another view of a CPU package with all of these pins or connectors that allow all of that input and output to and from the motherboard components. Whenever you have, if we use the extension of superhighways and multi-lane highways and traffic lights, the idea of an interrupt. So you have this concept of an interrupt where if you're controlling the flow of data between components, there are times where you need to kind of start and stop the process in order to prevent collisions and data corruption. So an interrupt is the digital equivalent of a traffic light. If you were looking at the roadway system of a metropolitan area. An IRQ, or interrupt request, is the operating system equivalent. On the software side, an operating system issues an interrupt request, or an IRQ, in order to interrupt the flow of data, or to hit the pause button for the flow of data while so many applications are running simultaneously. So in multi-user and multi-tasking operating systems, that becomes really important. Essentially, you have a hardware interrupt, then you have an internal one that's generated by a program. It's a software interrupt, and then you have a program-generated one that is used to transfer control to the operating system. So you have these three different kinds of interrupts, but basically the important thing to understand about interrupts is what they do. So they're like traffic lights that control the flow of programs where you're switching tasks, right? And your CPU switches tasks very, very rapidly. You'll need to be able to identify the different components of a system board or motherboard. That's part of the scope of our interest here. And one of the critical things we want you to do is to spend some time looking at different motherboard designs so you can get better at picking out the different components. So the key to that is to identify the CPU socket first, and then usually the smaller slots next to that, or where the RAM modules, the dual inline memory modules, or DIMM sockets, receive the memory modules, the DIMM modules, and those are right next to the CPU. But then further away are the expansion slots for other I/O. So in this view, you have the CPU socket here without a package inserted, right? And then you have the RAM DIMM slots. This is where the memory modules for RAM go. And then over here would be a lot of the rest of the input and output for that system. So you get better at this the more you view different motherboard designs, but they all have the same basic pattern, and they track with the von Neumann model. This last piece of information, or this last resource, is something we want you to become intimately familiar with. It's basically a table of memory types based on speed and size and cost. So as you move down the chart, the speed decreases, right? But the size of it increases. Static RAM level 1 or L1 cache, static RAM L2 or level 2 cache are both found on the CPU die itself. And so what you have is a case where you have you have some very fast memory. It works like RAM, but it's a little different. And because it's very fast, it's also very expensive. The closer you are to the CPU, the smaller it is, the faster it is, and the more expensive it is. The further away from the CPU you go, it's less expensive, and it isn't as quick, but it is much larger. So your capacity increases the furthest away you get from the CPU. That's the trend on this table. And what we'd like you to do is familiarize yourself with the different types of RAM and memory. There is a new type of static RAM cache. It's called S3 cache, L3 cache. And that L3 cache is often found on the package adjacent to the die. I'm sorry. L1 and L2 are found inside the processor, but L3 cache is found adjacent to the processor. So you'll see it sitting next to the core, but it's not part of the processor. The extra cache for performance built into some chip designs, the level 1 and level 2 cache. Level 1 is smallest, it's in closest to the core or CPU. As you get closer into the CPU, there's less and less capacity, but it's faster and faster because the CPU requires a very rapid pace of fetch, decode, execute, fetch, decode, execute, fetch, decode, execute. And in order to design that so that the hardware supports efficient CPU execution, you need temporary memory to store temporary quantities of data besides the registers on the CPU and apart from the RAM modules on the system board. So this special type of memory in between, again, is called a cache. System RAM is referred to as SDRAM, and oftentimes it has to do with dual data rate. And you have DDR3, DDR4, DDR5. So at this point in time you have faster versions of the system RAM. Just remember that SDRAM is the system RAM. We've already talked about programmable RAM as part of the BIOS chip. We'll talk more about this in our next session, but the important thing to understand is that you need to learn everything on this table and understand the trends. So the further down the chart you go, the larger the memory capacity, but the slower the performance and the lower the cost. So those are the trends. That's it for today. Thanks for joining us. We'll continue and pick up at the top of our next page, where we talk about progression of memory types in a different, a related graphic here. So this table and this graphic are related, and we'll refresh the information on this table and then talk about the diagram, the related diagram, in our next session.